big one. Yeah.
Yes, I just remember.
Oh, yeah.
I was like, wow, I was really unproductive in this. I totally forgot about food. For some reason, I thought we just had
All right, we have a lot to do today because I'm behind a couple of words, so I'm going to jump right into it. All right, we have to complete our discussion of emissivity. All right, you'll recall that emissivity, the last word that I did on Friday was emissivity, and we defined emissivity as simply the emissive power emitted by a real body compared to the emissive power emitted by a black body at the same temperature. We could also write this in terms of spectral emissivity. All right, so what are we going to do? Let's do a quick application here. Let's say that we have a real body. With the following emissivity profile. It looks something like this. So we have a certain emissivity here, call this emissivity 1, and that's between 0 and lambda 1. And then we jump from to emissivity 2, a little higher, between lambda 1 and lambda 2. And then we proceed with emissivity 3 out to infinity. Okay? Over the rest of the way. What's the total emissivity? All right, we have 3 different emissivities. How do we come up with the total emissivity? Well, what we do is this. We recognize that the emissivity is going to be equal to the integral from 0 to lambda of the emissivity of spectral emissivity times E lambda B, just E lambda, excuse me, over sigma t to the 4th, which is our total emissivity, black body emissivity, and that's times d lambda. And we're going to integrate that. What we're going to do is we're going to integrate it first, and it's going to be equal to this. That's going to be equal to E1, which is a constant between 0 and lambda 1. Okay? And 0 to lambda 1 of E lambda B, E lambda B d lambda over sigma t to the 4th plus lambda 1 epsilon 2 times the integral integrated between lambda 1 and lambda 2 of E lambda B d lambda over sigma t to the 4th plus epsilon 3 from lambda 2 to infinity of E lambda B d lambda over sigma t to the 4th. What is this? That is correct. That is f from 0 to lambda 1. So this is equal to E1 times f from 0 to lambda 1 plus epsilon 2 f from lambda 2 lambda 1 to lambda 2 plus epsilon 3 times f from lambda 2 to infinity. Now, this one we can look up in the table, right? If we know lambda 1 and we know the temperature. This is a different story. This is where we're going to have to go back to what we learned in the previous class, and then I'll ask how we deal with this. This will be equal to E lambda 1, epsilon 1 times f 0 to lambda 1, which is a lookup, plus, how do we deal with this one? Lookup. Yeah, well, E epsilon 2 times f from 0 to lambda 2 minus f from 0 to lambda 1. Right? Same difference? Not the last one.
Find where it stops a minute and then
No. Much easier than that. Anybody know how we deal with the last one?
1, 0 to infinity.
We're getting close.
0 to infinity minus 0 to
Thank you. Which is 0 to infinity is what?
1.
1. So that's now we can look at that. That's the same. Then we look at these, and we can get it, and we come up with a value for that epsilon. And then the total emissivity, or excuse me, the total emissive power, E, is going to be equal to this averaged emissivity, which we just solved for, times EB all right, and that's how you do it. Any questions? All right. Now let's move on to some of that's really about the last of our definitions, if you will. And now we get into the fun stuff of radiation. And the fun stuff is it's like a puzzle. It really is like a puzzle. For those of you who like puzzles, you're going to find this very interesting. For those of you who do not like puzzles, you're going to find this very annoying. Okay? If you like puzzles, you're in good shape. Yeah, like Sodexo and Sodexo delivers foodstuffs to stores. Dewey, got some homework for you. Cody, I got homework for you. JJ is still at the eye doctor. Where's Hudson Petro? We don't know.
Sleeping off U Festival.
Sleeping off what?
U Fest.
Was this weekend, spring weekend?
Yeah.
Is that fun?
Yeah.
Is it really? Well, you can't drink or anything, can you?
Not at all.
No, you drink outside.
What do they let the seniors drink?
They let the seniors and juniors drink.
Oh, if you have a tag? A few years ago, they had like this spontaneous flash riot down at Bakeland. Have you heard about it? Yeah. Bayside, yeah. Yeah, they didn't know what to do with it. Everyone was out drinking and partying, and they didn't know what to do.
That's exactly where you guys came from. Oh, really?
Yeah. Time survey. I did take pictures of everyone though.
So they could light them up afterwards.
Yeah, I think so. I don't know whatever happened. Fortunately, I'm on the other side of that fence and I stay there. Believe me. No, I was not down there partying. All right, today we do radiation view factors. All right, radiation or shape factors, view factors. This is interesting stuff. We already know that how much radiation a body receives is going to be how it is viewed from other bodies. So, and depending on the literature, what we're studying today is known as view factors or shape factors. So you see both those terms used. All right, now stay with me. This gets a little, this is a little complicated to begin with. We're going to do this to begin with for a black body because it's easier. Okay? We're going to have two bodies, two surfaces. There's surface 1, some area A1, and some temperature T1. Oh, I'm sorry, I make it I. And over here is an area AJ and some temperature TJ. All right. Now, we're going to look at a small differential element on this surface, and we're going to connect these like so. That'll be a connector between the two. And then, oh, I get my areas. So. All right, and then how does this little differential area see that little differential area? Well, I'm going to take and draw lines like this. So from the center of this little differential area that sees this differential area like this, this is, anybody know? That is omega. That is my solid angle. So this is omega. So this will be d omega ji. So d omega, describing surface J as seen from surface I. Okay, so this is my solid angle. I'm going to put normals on here. So here's my normal. This is my normal I. And this will be my normal J, like so. All right, and let's see what else I have on there. Oh, this distance here, from here to here, this is R. The distance between the center of the two surfaces. This is dAI. And this is dAJ. Okay? Well, let's see what else here. Oh, the distance between, the angle between the radius and the normal will be theta sub I. And here, this will be theta sub J. And these show as normals. And have I left anything out? No. Now, black bodies. So, I have EBI times AI is going to be the emissive radiation rate to all space. So if I know this entire area of AI, and I know the emissive power of that surface, it's a black body, then I know how much emissive power is being radiated all space, correct? Okay? All right. I am going to define Q, I, J, bear with me because these subscripts get a little complicated. So in other words, the heat transfer leaving I, which strikes surface J, is going to be equal to EBI AI times Fij. And Fij is going to be the fraction of radiation leaving AI strikes AJ. Okay? And our quest is going to be to solve for this. And that's really the quest for the rest of the semester. Pretty much that's it. And it's like a puzzle. It's like a puzzle. Some are good at solving puzzles. Okay. Now, how are you going to do this derivation of Fij? All right. You will recall from an earlier lesson that we defined dq. In this case, I'll subscript that dq I to j. In other words, the heat transfer leaving q that strikes j as being equal to the intensity E times dAI times the cosine of theta I times the solid angle d omega j to I. That was your first homework problem in radiation, I believe. And we said the solid angle d omega j to I can be described as the cosine of theta j dAj differential divided by r squared. So now we're going to substitute that into the top, and we end up with dq I to j is equal to IE dI AI times the dAI. Let me rewrite this. Cosine of theta I times the cosine of theta j over r squared d theta I d no theta I d AI d a j. Correct. Okay? So all we've done is we've taken this basic definition we introduced in the first class and the definition as well for the solid angle, and combined the two together, given the parameters of the drawing we have on the board. Okay? Now, okay. Now for a diffuse emitter, and the black body is a perfect diffuse emitter. Remember, right now we're just talking about black body. So, a perfect diffuse emitter. We know that E, or I, E, is not equal to a function of theta, and therefore I BE is simply equal to EBI over pi.
Should be not function of theta, right?
Thank you. I think I said it, I just didn't write it right. All right. Okay. So now we're going to substitute integrate. So, we're going to substitute in here, and EB can come out because that's a constant for a black body. So we end up with QI to J divided by EBI is going to be equal to AI FI to J. From down here, that's what you're reading. Okay? And that's going to be equal to the double integral over A, first over AJ and then AI. And that's going to be the cosine of theta I, cosine of theta J over R squared, pi R squared, dA J, oh, excuse me, DAI, DAJ. All right. Next. Okay.
Shouldn't the I and the J be reversed?
Pardon me?
Shouldn't the DAI and DAJ be reversed? Because the
Oh, because the order of integration? Yes. Not that, I don't think it really matters, but yeah, it's neater that way, you're right, because you integrate from the inside out. All right, fair enough? Now, let's stop what we're doing for a moment and go back and imagine that we completely redraw the whole thing. Okay? But now, we look from this little differential area AJ over to I, and everything is reordered. Okay? Well, if we do that, we come up with the following result. And the following result is this, that Q, J to I, divided by E, B, J is equal to A, J, F, J to I, which is equal to the double integral what are those? They're exactly equal. All right? So what does that mean? That means that this term and this term must be equal. Okay? Now that's important. And this is known as reciprocity. This is a reciprocity theorem. And you will use this a lot as you solve these problems. In other words, the area of a surface emitted times the view factor of how that surface sees another area is equal to the other area, which is emitting, times the view factor of how that area sees the first. And that's called the reciprocity theorem. And a relatively abbreviated proof for your pleasure. That's your first tool in your toolbox. The first tool. We have many more tools. Okay? So of course the tools. All right. Let's continue this and finish this discussion. If we do this, and we're going to say let Qi to j is going to be, we're going to define Qij, just Qij. Now notice that we are taking the dash out. So Qij, let me write that a little clearer. We're going to define Qij as being equal to Q, I to j minus Qj to I. So what is Qij? No, what is it in terms? Describe it. What?
The net heat transfer?
It's the net heat transfer between the two surfaces. All right? It's the net heat transfer between the two surfaces. So it's equal to what leaves I that strikes J minus what comes in from J striking I. Okay? So it's, Scott said, it's the net heat transfer between the two surfaces. All right? So Qij is going to be equal to Qi to j, which is EBI AIFI to j minus EBJ AJFJI, or Qij is going to be equal to AIFI to j times EBI minus EBJ. Right? Because IIFI to j, IJ is the same as AJ, well, you could get confused, same as AJ, FJ to I. Okay? And if you go back to the first day of class, when we introduced the 3 modes of heat transfer, that was the last one for radiation. All right? Which was basically that the radiation, net radiation exchange between two surfaces is going to be equal to the difference in their temperatures to the core. All right? Now, that's very useful. We now have a way of being able to describe the net radiation transfer, or net radiation heat transfer to or from, depending on whether or not it's positive or negative on a surface. Okay? However, it's only the very beginning, because in the next, today is 37. We have 38, 39, 40, and 41, right? We have 4 more lessons left. We use them all. All right, so in the next 4 lessons after this, we start looking at exchange from multiple surfaces. Next time we just take 3 surfaces into account, and then it gets interesting when we take an infinite number of surfaces into account.
Just superposition?
No, we use an electrical analog as the technique and a series of linear equations to solve the problems. Okay, so that's coming. Something to look forward to. I don't want to get boring at the end of the semester. All right, so any questions on this? All right, so now what do we have to find? We have to find these shape factors, F's. All right, we know from reciprocity. Now, what happens is, what's interesting is this. This theorem is very useful when one surface sees another surface entirely. All right, I got a black box and I got a little disk inside. The disk inside sees the inside of the black box. What's its shape factor? Assuming the disk is flat. What's the shape factor for the disk seeing the box? Okay, I've got a black box enclosure. Inside I put a disk. And I say, what is the shape factor of how the disk sees the box? 1. All right? So if I know the area of 2 and 1, then I can tell you how the box sees the disk. Okay? Which is complicated because the box sees, there's 6 sides in a box. The box, each side sees itself. Or sees the other sides. Okay? If it's flat, unless it's concave, convex, it doesn't see itself. Okay? All right. Alrighty, so where are we here? Okay, so other view factor relations. All right, so number 1, we have the reciprocity theorem. And we already know what that is. That is AI Fij is equal to AJ Fji. Okay, that's the one we just finished. Now let's talk about summation. I already mentioned on that. In an enclosure, of J equal 1 to n surfaces, so total of n surfaces, then the summation from J equals 1 to n of Fi to j must be equal to 1. Okay? That's another tool.
What's that 1 comma n? I don't.
J, there are 1 to n j surfaces. So you'd have j would equal 1, n equal 2, equal 3, equal 4, equal 5, n. Okay? Some arbitrary number.
So you can have an enclosure of 1 surface?
I'm sure.
So that's the disk against the black body because then there's only like one surface.
I have to think about it, but yes. The answer must be yes, because it certainly is that way, but we just have to think about it. Can't give you, what'd you say, Patrick?
If there's a disk against the black body, you're only counting one surface, because the black body and the other side of the disk are next to each other, so there's no rotation. So we have to be only one surface, because there's only one surface.
I think the answer is that if you're going to have an enclosure, you're going to have more than 2 surfaces. The only exception to that might be if you're in a sphere. okay? Then a sphere would have, that'd be an exception, right there. A sphere would be one surface. That'd be an enclosure of one surface. But it's kind of trivial. It's kind of trivial in that case. But at the same time, in order for that to hold, you've got to start with the counter with 1. Okay? But Patrick, nice try. But I think the sphere would be the enclosure of one surface. Okay? Alrighty. So this is 1. So all your shape factors have got to add up to 1, or 1 for a surface. Okay? All right. 2 or 3, common sense. All right, common sense. F, I to I. Now that is how a surface sees itself, by the way. How a surface sees itself is equal to 0 for a plane surface or a convex surface. And F, I to I is greater than 0 for a concave surface. Or a sphere. A spherical enclosure, for example. Sees itself. All right. And then the last, and where I think it really gets interesting, is just your algebraic approach. All right? Let me give you an example. Let's take a surface. We'll call A1. And over here, we'll have the 2 surfaces, A2 and A3. All right? Now, we can write this like so. We can say that A1, F1 to area 2 and 3 combined, okay, is the same as A1 times F1 to 2 plus A1 F1 to 3. And using this is very, very useful. And we can also write A2 to 3, that is this total area, sees F2 to 3 to 1. In other words, how it sees 1 would be the same as how A2 sees 1 plus how A3 sees 1. Now, your 5th tool in your toolbox is in your textbook. And these are tables 13.1 and 13.2, and figures 13.4 through 13.6. So let's take a look at this for a moment. Open your textbook to those pages, or to those. It's table 13.1 starts on page 831 in edition 6. In general, I do not suggest you use these tables unless you really, really have to, or in this, the complicated formulas. They show you parallel plates, they show you inclined plates, they show you perpendicular plates with a common edge. They show you 3-sided enclosures, parallel cylinders, a whole bunch of different shapes. And then 13.2 has view factors for 3-dimensional geometries, for aligned parallel rectangles, coaxial parallel disc, and perpendicular rectangles with a common edge. However, as you can see, those formulas are ripe for a miscalculation. So what is much easier to do is to flip the book over to figures 13.4, 13.5, and 13.6. And this is what I would expect you to use when you're solving problems. You'll see that you have the three-dimensional figures in table 13.2 at your disposal. And what you do is you calculate the different parameters as shown in the diagrams, and then you read the shape factor of the curves. So you go up the curves, and then you read over and you read the shape factor on the y-axis. Okay, any questions? Let's do a remaining time. Let's do a quick example problem. Let's take following diagram. All right, this is a 90-degree angle, and this is surface 1, surface 2, surface 3, and surface 4. You know the dimensions of all the surfaces, all right? And you are to find F1 to 4. How does this surface see that surface? This is where it gets to be a puzzle, all right? All righty. So I'm going to go through this kind of quickly. We know that A1, 2, that is the common area, sees 3, 4. So we have A12 sees area 3, 4. 3, 4. Okay? So how does this see this? Well, first of all, if you know all the dimensions, where can you go to look up that shape factor? How about figure 13.6, right? 13.6. So you can look this up. This is a known number, okay? This is a number from, well, I don't want the whole number. I just want this. So F1, 2 to 3 to 4 can be obtained from table 13.6. Agreed?
Yeah.
All right. Now, let's do the next one. You can also get F2 to 3 from table 13.6. And you can get what else? You can also get F2 to 3, 4. Agreed?
Yeah.
All right. So now we're beginning to cook with gas. All right. So we have F1 to 2, F3 to 4, F2 to 3, and F2 to 3, 4. All right. So we know all those shape factors. All right. If we know those, we can, let's see. We can also get F.
3 to 2.
You can also get F. There's a couple of different ways to solve this. You can also get F1 to 2 to 3. Okay? Yes.
Are we using A 1 to 2 for all of those?
No, I'm just saying these shape factors, no, this is just the first relationship I wrote down. And then from that, I just said you can get this value in table 13.6. You can also get this value in table 13.6. And you can get this value in table 13.6. And you can get this value in table 13.6. And I'm almost out of time. So I'm going to just whet your appetite and I'll leave that for you. With all those values, you can then start breaking things down like I did here and here. And you can start solving for the unknowns, and ultimately, you'll be able to solve for F1 to 4. And that's what your homework is all about tonight. Solving these puzzles. These puzzles are a lot of fun to solve. Unless, of course, you happen to be a student with hours and hours of homework and you jump flying, starting down alleys, stopping and going back. Particularly exciting. Patrick, you have a question, a burning question. Thank you, sir. That's figure 13.6, not table. Thank you, Patrick. So, I don't know if there is a table 13.6, to be honest with you, but these are figures. All right, any questions? Let's see, anybody here that came in at the last minute? Alex?